Video problem 87, the pH scale. Determine the pH of the following weak bases. So we have a 0.25 molar solution of B minus. The Kb is equal to 1.8 times 10 to the negative fifth. First, let's write the dissociation reaction, or the base reaction. It's going to look like this. I'll write it up above here. B minus, which obviously that's aqueous, plus H2O, liquid. Right, a base is something that accepts a hydrogen ion. It's weak, so we have the two-way arrow. So it's going to be Hb, aqueous, plus hydroxide. Right, that means, switch to a black pen here, that means that my Kb is going to be equal to Hb times OH minus all over B minus. Remember, water is a liquid, so it doesn't go into the equilibrium expression. And this is equal to 1.8 times 10 to the negative fifth. Okay, so let's see, it's a 0.25 molar solution. I'm going to have to use an ice table here. So let's go ahead and write out the ice table. So we have B minus, Hb, and OH minus. B minus starts out 0.25 molar. No Hb, no hydroxide, so those are going to go up by some amount x. This is going to go down by some amount x. So my equilibrium is 0.25 minus x, x, and x. Now, just as we did last time, we can assume that that's really, really small, so we can assume that it's close to 0. So I can plug these values back into my equilibrium expression, which is going to be x times x over 0.25, and that's equal to 1.8 times 10 to the negative fifth. So let's go ahead and do this problem. 1.8 times 10 to the negative fifth times 0.25. So I get a value of x squared equals 4.5 times 10 to the negative sixth. Take the square root of both sides. And I get a value of, for my x, 0.00212. Now, what does x represent? We always want to say what x represents. So x is equal to concentration of hydroxide or concentration of Hb. Of these two, I'm really only concerned with the hydroxide. But let's go ahead and do our 5% check first. So we assumed that this x was 0 or close to 0, and then we have to check that with the 5% rule. So I'm going to go ahead and do that over here. I'm going to take 0.00212, which is the amount of hydroxide I have, divided by 0.25 times 100. If it's greater than 5%, I have to go back in and use the quadratic formula. But this one is much smaller than 5%. This one is only 0.849% ionized. So my assumption is good. So I'm going to take this, and I'm going to find the pOH, because remember, this is hydroxide. So my pOH is equal to 2.673. I'll use 2 sig figs. So my pH is equal to 11.33. Right. Let's look at this next one. Now this one I'm given the grams of methylamine in 10 milliliters of stock solution. Let's go ahead and write out the base reaction here. So that's methylamine. It's going to be CH3 NH2 plus water. Okay, the base, that should be an arrow. Let me try that equilibrium again. Come on, you can do this. Maximum effort. There we go. So the base is going to accept a hydrogen ion, and that's going to leave me with a hydroxide. Okay? So I can set up my KB expression. Just a quick hint, you're going to need lots of room for this problem, so just letting you know. Alright, well first we have milligrams, but I need to know the molarity, so I need to get it to moles per liter. So let's convert our milligrams to moles first. So 2.5 milligrams of CH3 in H2. The molar mass of this is 31.06, but let's get it to grams first. 1 gram, 1,000 milligrams. Okay, so there's grams. Milligrams cancel out. So 1 mole is 31.06 grams. So let's see what we get. We get 2.5 divided by 1,000 divided by 31.06. So that gives me a value of 8.049 times 10 to the negative fifth. So that's moles. Divide by liters, 0.01 liters. And that'll be the initial concentration. So that's the initial concentration of that methylamine. Right. Let's go ahead and use our ICE table. Let's go CH3NH2, CH3NH3 plus, and hydroxide. Alright, so the initial amount of this is 0.008049. So let's do 8.05 times 10 to the negative third, 0, 0. This is going to go down by some amount x, up by some amount x, up by some amount x. So this ends up being 8.05 times 10 to the negative third minus x, x, and x. I'm going to assume that that is less than, that's pretty small. So now let's plug everything into our equilibrium expression here. This is equal to 4.38 times 10 to the negative fourth. So I get x times x all over 8.05 times 10 to the negative third. Remember that minus x we said was close enough to 0. Now I'm going to tell you what x is here. In this case, x is 0.00188. Okay, that would be the molarity, which is the concentration of hydroxide. Let's go ahead and do our 5% check, because I can see this is pretty big compared to this. So our 5% check is just going to be 0.00188, which is the molarity of the hydroxide, divided by 8.05 times 10 to the negative third, which is the original molarity of the base, times 100, and we get a value of 23.33%. Now that's much greater than 5, right? So what does that mean? Well, that means that I cannot ignore this minus x. I have to go back in and put in that minus x. Alright, so I'm actually going to scroll down here and do this problem. Okay? So I'm going to start scrolling down here. I'm going to start right here where it says Kb is equal to concentration of CH3 in H3 plus times the concentration of hydroxide all over the concentration of CH3 in H2. Now I need to plug in x, x, and 8.05 times 10 to the negative third minus x. Okay? So, let's finish my Kb expression here. That Kb is actually equal to 4.38 times 10 to the negative fourth. So I've got x times x over 0.00849 minus x. That's the x that I usually drop. I can't drop it this time. Okay, so I end up with something that looks like this. I'm going to multiply both sides by 0.008049 minus x. So those cancel out. Multiply over here, 0.008049 minus x. So this becomes x squared is equal to 3.525 times 10 to the negative 6th minus 4.38 times 10 to the negative 4th x. Okay, now I want to get everything on the same side, so I end up with this 0. So I set it equal to 0 because I'm going to do a quadratic formula here. 0 is equal to x squared plus 4.38 times 10 to the negative 4th x minus 3.525 times 10 to the negative 6th. Right. So that's my A, that's my B, that's my C. So now I'm going to plug this into the quadratic formula. Alright. So here's the quadratic formula. X is equal to negative B plus or minus square root of b squared minus 4ac, and that's all over 2a. Okay. So let's plug it in. X is equal to negative 4.38 times 10 to the negative 4th plus or minus square root of b squared, which is 4.38 times 10 to the negative 4th squared minus 4 times a, which a is 1, times c, which is negative 3.525 times 10 to the negative 6th, and that's all over 2 times a, which is 1. Alright, so this is square root. So it's a big one. So I get to this. X is equal to negative 4.38 times 10 to the negative 4th plus or minus 0.00378 all over 2. So I get two different values for x. One value for x that I get is 0.001671, or I also get a negative 0.002109. Well, you can't have a negative value, so that can't be true. So this is my x, and again, let's identify what x is. So that is the concentration of hydroxide. Okay, so if we scroll way back up here, we can see that x is the concentration of hydroxide. So that means I can take the negative log of this value to find the pOH. Get my calculator out. So I get a pOH equal to 2.78 and a pH then equal to 11.22. So there you go. There's an example where the percent ionization is greater than 5%. So that shows you what all we have to do if it's greater than 5%, and it basically comes down to the fact that I can't drop this minus x, okay, because that x is significant. Right? It's big enough to be significant. All right, let's go up and do C. This one won't be nearly as long. Okay, we have a solution of pyridine. Right? So let's write the reaction first. Pause it and make your own prediction of what the reaction is going to be. So there's the reaction. Okay. I can write a KB for this. Okay, so there's my KB expression. That's a 9. If we're going to do an ice table, which we need to because we don't know any of the equilibrium concentrations. We've got hydroxide. I've got C5H5NH+, and I've got C5H5N. So I've got 0 and 0. This starts out 2.45, which is pretty big, plus x. This is going to go down x. And again, remember, how do we know which is plus and minus? Well, I can't get smaller than 0. So that's how I know that it's plus. Right? And if the products are increasing, the reactants have to be decreasing. So it's x, 2.45 minus x. That minus x I can drop. So when I plug it in here, I get x times x all over 2.45. So I got 1.7 times 10 to the negative 9th times 2.45. So I get this, x squared is equal to 4.165 times 10 to the negative 9th. Okay. Take the square root of both sides. So I get a value of 6.45 times 10 to the negative 5th. Let's go ahead and check the 5% rule here just to be certain. So that's going to be the amount of hydroxide, which is 6.45 times 10 to the negative 5th, over the original concentration. I can easily see that this is not going to be even close to 5%. So yeah, I get 2.63% times 10 to the negative 3rd. 2.63 times 10 to the negative 3rd percent. So obviously I'm okay here. So let's clearly label what X is. X is the concentration of hydroxide. It's also the concentration of C5H5NH+, and we're not concerned about that now, but later on we might be. Right? So I can calculate the pOH. So my pOH is 4.19. My pH is 9.81. 2 sig figs. Yeah, 2 sig figs.